This presentation is delivered by the Stanford Center for Professional Development.
Well, I guess we'll just continue. Oh, well, no, we'll wait. Just continue. So last time we looked at localization methods. So in the basic idea of a localization method, I mean, you can think of these as just generalizations of bisection. They're generalizations to Rn. So you have bisection in multiple dimensions, and it's not a simple, there's no simple extension to Rn of bisection, because in R, first of all, convex sets are kind of boring. They're basically just intervals, right? So, and there's an obvious center of an interval. In Rn, things are much more complicated. You have many different centers. Say, I don't know if you have that pointer somewhere. Where is it? Ah, there we go. Okay, thanks. Okay, so the basic idea is you have some polyhedron where you know the solution, if it exists, to lie. And you query a cutting plane oracle at the point x, and what comes back? In this case, this is a neutral cut here. In other words, what it's basically telling you is that you need not even consider anything over here. So the solution is not here if it exists, and so this is your posterior or updated ignorance set, or whatever you want to call it. It's the set of points, or localization set. It's a set of points in which, if there is a solution, you know it must lie. Oh, I should mention one thing. The lectures are, there's more material on this, of course, in the notes, which you should be reading. So, and we're expecting everybody to be reading. Okay. So, bisection on R is the most obvious and well-known example. Let's look at some other ones. We'll look at some of these in more detail today. So, the first is the CG method. I just got up to that at the end of last lecture. Here you have xk plus 1 as the center of gravity. I'll review that quickly and say a few things about it I didn't get to say last time. Others would be maximum volume ellipsoid, Chebyshev center, Analytic center. These would be some of the other ones. And we'll talk about each of those in a little bit of detail. Okay, so the CG algorithm uses a CG of a set as your query, of the polyhedron as your query point. And there's an amazing fact. In fact, we may even, if we can find a simple enough proof, we'll stick it on homework 4, which we're working on. And then the amazing fact says this, that if you take actually it's any convex set. You take any convex set in Rn and take the center of gravity of that set and then pass any plane through that point. Then the question is, how unevenly does it divide the volume? So, and you might guess the answer is 50-50. I mean, for example, in R, it's 50-50. But it turns out immediately you can draw a couple of pictures in R2, and you'll see that, in fact, there are points. There's no point. You can make a convex body for which there's no point for which all lines going through it divides the area 50-50. But it turns out you can't skew it too much, and it turns out that the actual ratio you can go to is like 0.63, 0.37. So it's roughly, it's not even 2 to 1, right? Because it's this divided by 0.37. Not even 2 to 1. It's more like 1 point something or other to 1. And that means basically, if you find the CG of a set, it can, and you put any the worst hyperplane through that point will chop off at least 37% of the volume. So that's what it is. Okay. So that says in the CG algorithm, that's very nice because it says the volume of the localized set goes down by the factor 0.63 at least. It goes down by that. It can go down more. If you have a deep cut, it goes down by more. And of course, this is the 0.63 is the factor for the absolute worst possible hyperplane at each step. And in fact, it can be, it obviously is typically much less or something like that. So that's that. We looked at the convergence and and look through various things. We came at the last minute to, basically the problem with the algorithm. The problem with the algorithm is that computing the CG is extremely difficult. So the whole thing, it's a conceptual algorithm is what it is the way it's described. Now, you can modify the CG method to work with approximate CG computations. I'm going to mention some of those because there's some very cool new work, not from Moscow, from MIT, the new Moscow. And it's very, very cool stuff. I'll say some of that. Obviously, you don't have to compute the CG exactly. So first of there are methods even from the 60s where a cheaply computable approximation of the CG is given, and then you have a chopping, a slicing inequity theorem, right, which is not as strong as the 0.63, but is enough to sort of give you convergence and so on. So those you already had in the 60s. So those are approximate CG methods. But let me just mention actually a really cool method developed, I don't know, 4 or 5 years ago, something like that at MIT. I mean, it's by people at MIT. Very, very cool. It goes like this. You want to calculate the CG of a convex set. And you're going to use a randomized method. And the randomized method is called hit and run. I don't have any, has anyone heard of this? Or, okay, it's just very cool. So this is an advanced class, so I can go off on a weird tangent and tell you about it. So the way it works is this. You have a point, and you generate a random direction. So you generate a random direction, and you make a line. And you need the following. You need the ability to find out where that line pierces your set. So that's what you need. So here's your set. I'll make it a polyhedron, but it does not have to be a polyhedron. It's just any old convex set. It doesn't really matter. Here it is. Here's your set. And you take a point here, and you generate a random direction. Actually, how do you generate a random direction? Uniform on the unit sphere. How do you do that? How do you generate a random direction? Uniform on the unit sphere.
Uniform in...
What's that?
In 2D, I guess just...
No, I thank you for bringing it up. I should say, calculating the CG in 2D and 3D is like no problem at all. 2D is trivial. All you do is you calculate, you find a point in the set, you calculate a triangulation of the polyhedron, done. In 3D, same thing. However, it's going to scale sort of exponentially in the dimension. So if you're interested in 2 and 3D, CG is a non-problem. Okay, so how do you generate a random direction, uniform on the unit sphere? Or just a random variable, uniform on the unit sphere? What's it?
Choose a random vector and normalize it.
Yeah, fine, but I mean, how do you choose a random vector? What distribution?
Gaussian.
Why? Because you can't think of any other? Or, I mean, you happen to be right. If you choose a random Gaussian vector, right? So it's N0I vector. That's circularly symmetric, and so if you then normalize that, you get a uniform distribution on the unit sphere. So you choose a random direction here, and so here's the line you get. And the only thing you need to do is to calculate these two intersections, okay, which is very easy to do. Okay. Now you do the following. You generate a random variable uniform on this interval, and that is your new point. So that's going to be right here. And you repeat. So you go here, you calculate a random direction. The direction turns out to be this. You do a random random point on there, and you get there, and you go on. Okay, so I suppose these are the hitting points, and this is the running, or who knows anyway. I don't know how that name came up, but that's what it is. Okay. Everybody got this? So that's a Markov chain. It's a Markov chain propagating in the polyhedron, and it actually it converges to a steady state distribution that's uniform on the polyhedron. Okay. So that's a method for calculating. That's a method for generating a random variable that's uniform. By the way, if you have a method that calculates a random variable that's uniform on a set, how do you find the CG? What's that? Thank you. You just average, right? So, let me ask another question. Anybody got other ideas for how to generate a random point in a polyhedron? A uniform distribution? How would you do it?
Generate a random distribution everywhere.
Okay.
And reject the one that are outside
Fine.
your set.
All right, so but it couldn't be everywhere because it has to be uniform. Okay, so what you do is you find a bounding box. Everybody knows how to find how do you find a bounding box for polyhedron? Oh. This is the problem with scheduling class at 9:30. It's before full outer cortical activity has warmed up. How do you find the bounding box for a polyhedron?
Minimize first coordinate L1.
Thank you. So you minimize x1, then you maximize x1. You minimize x2, then you maximize x2, and these are like LPs or something. Of course, maybe we're trying to solve an LP. I don't know what we're trying to do, but still, that's how you do it by solving two n LPs, right? Okay, so you make a big bounding box like this, and now you generate a random, a uniform distribution on that, right? And you do that by taking a uniform distribution on each edge and sticking them together. Okay, and then you reject the ones that are outside this thing. And the ones inside actually then are, that is indeed, those points are drawn from a uniform distribution on the polyhedron. Okay? Any comments on how you imagine that might scale with dimension? And let's say you had the bounding box.
Exponentially with the number of them.
Which way though? Exponentially what? What would happen exponentially? You're right, something happens exponentially. What is it? Well,
to test if the point is in the polyhedron, or
no. To test if a point is in the polyhedron, you form AX. You give me X, I calculate AX, I check if it's less than or equal to B. That's fast. What happens?
Volumes.
There you go. Ratio of volumes, in the worst case, goes like goes down exponentially, and that means you'll generate exponentially many random points before you even get one in the set. So although that does indeed produce a random, it does produce a uniform distribution on the set, it's not going to scale gracefully to high dimensions. Right. Okay, so anyway, so this is the hit and run method. There's lots of you can certainly do a cutting plane method with something like this, and there are more sophisticated versions, but that's it. Okay, so that's the CG method. Yeah.
The vertices where it intersects.
Oh, here? Oh, that's actually quite straightforward. If this is a polyhedron, let me show you how that calculation goes. So the calculation goes like this. Here's your polyhedron. It's defined by that inequality. So AX less than B. You're given a base point x0 and a direction v. And you want to find the maximum and minimum values for which this holds. That holds for t for an interval, right? Oh, so I'm assuming this is bounded polyhedron. I'm assuming x0 is in the polyhedron, although none of that matters. But anyway, so that says that a x0, that's what t equals 0, is less than b. And now you want to find how much can you increase t until this becomes false, and how much can you decrease t below 0 until it becomes false, right? That's the question. So you just write it this way. It's actually kind of dumb. You write ax0 plus t times av is less than or equal to b, like that. That's a vector. That's a vector. Now it's very easy to work out the maximum. Because this is basically, let's see. Let's call this a plus t b. No, that wasn't a good idea. How about a plus tc is less than b? There we go. Now it's going to work. Now it's extremely easy. What you have to do is this. If I increase t, this thing, by the way, if a ci is negative or 0, increasing t doesn't hurt any. It can't. We're not going to get into trouble there. So if I want to know how high can I increase t here, I only focus on the positive entries of c. So I first look at the positive entries of c, and I divide them by a or something like that, and then I take the min or something, and that's my, well, something. I do something, a minus b. Anyway, it's a 300 level class. I don't have to, I can just say it's easy to do. Does this make sense though? So you reduce it. So in fact, when you actually do this, it's like two little lines of something, little calculation. Okay. Okay. Maximum volume ellipsoid method. This method is not a conceptual method. It's a real one. Actually works really well. And here, xk plus 1 is the center of the maximum volume ellipsoid in pk, which I don't know if you remember or not, but that can actually be computed with that can be computed by solving a convex problem. By the way, how about the minimum volume ellipsoid method? In that case, you calculate the minimum volume ellipsoid that covers the polyhedron. Let's have a short, it's going to be a short discussion. Tell me about the minimum volume ellipsoid method. I don't know if you remember this, but you can kind of guess. Any comments on the minimum volume ellipsoid method? By the way, it would work very well. In other words, you'd get a guaranteed volume reduction, everything. Yeah, in fact, finding the minimum volume ellipsoid that covers a polyhedron defined by linear inequalities is actually hard. So that method is like the CG method. I gave you enough hints that you could figure it out. Did you actually remember that?
On the same problem and we got stuck. And then we remembered that it was very hard.
Oh, then you remembered.
Yeah.
Okay, good. So, okay. So that's a short discussion of the minimum volume ellipsoid method. But the maximum volume ellipsoid method is actually it's not a conceptual method. It actually works very, very well. And in this case, the volume reduction you get is actually very interesting. And the volume reduction is this. It's not a fixed, the guaranteed volume reduction is not a fixed number, as it is in the CG. In the CG method, you will reduce by 37%, end of story, any dimension. In this case, your volume reduction guarantee degrades with dimension, like this. By the way, it degrades gracefully enough that this method can actually be used to construct a polynomial time convex optimization method, right? Because a good enough approximation of the maximum volume ellipsoid can be calculated in polynomial time and so on and so forth. And this is also called, it's got like 4 initials, T, K, H, and 4 Russian names go together. E, K, Ehrlich. Anyway, I won't attempt it. Actually, I think it's described in the notes. Now, once you know that you get this volume reduction, you can work out a bound on the number of steps required. In this case, it scales not like n, as it was before, but it's actually n squared here. So this one degrades. And this is actually quite a good practical, perfectly good practical method. Okay. Other ones, I mean, you can pretty much make up your own method here. Chebyshev center method, I thought I'd mention it. It's now the problem with the Chebyshev center, that's the largest Euclidean ball in PK, and that's solved by an LP, by the way. That's a linear program to calculate the maximum volume ball that fits inside an ellipsoid is just an LP. Now this one, however, is not affine invariant. In other words, if I take my original problem and I do a linear change of coordinates, if I just scale, actually, if I scale the variables, maximum volume ellipsoid, the CG, you get a commutative diagram. In other words, if you take a polyhedron and you subject it to an affine mapping, you multiply it by T and add some S or something. T's a non-singular square matrix. Then the CG will also change coordinates exactly the same way, because CG commutes with an affine change of coordinates. Okay, so that means that the CG method is actually affine coordinate change invariant. Okay, the same is true of the maximum volume ellipsoid. If I give you a set and ask you to find the maximum volume ellipsoid inside it, if I then change coordinates by an affine change of coordinates and ask you to do it again, it commutes. So the maximum volume ellipsoid that fits in the transform thing is the transform of the maximum volume ellipsoid that fit in it or whatever. So that was my verbal way of drawing a commutative diagram. Now, the this has a number of implications. First of all, for our complexity theorist friends, I mean, this is of course extremely important. But it actually has lots of practical implications, and they're quite serious. Basically, if you have a method that's affine invariant, in practice, what it means is scaling of variables is a second-order issue. Now, in exact arithmetic, of course, it's a non-issue, but it means it's a second-order issue. It's a second-order issue because scaling can hurt you, but only through numerical round-off and things like that, and therefore, being off by a factor of 1,000 in the scaling of your coordinates, and no one gets hurt, right? Whereas a method like Chebyshev center here, I guarantee you, if you have your Chebyshev method, the center method working really well, and I apply, and I scale, for example, the first and the 8th coordinate by a factor of 1,000 to 1, your method is not going to work basically at all now. So that's the basic point there. Okay. So now, having said that, I should say this: if you're solving a specific problem class where you know what x1 is. X1 is measured in meters per second, and it varies between plus minus 5. X7 is a pitch rate in radians per second, or something like that, or radians per second squared, or something like that, or something like that. And you know how it scales. So in actual specific practical problems, the whole business of affine invariance may not be that relevant, right? Because in a specific problem, you generally know what the numbers are, what the ranges are, and things like that. Okay. All right. Now we'll look at one, and we're going to look at this one in considerable detail, actually, in the next lecture, because it's one that this one seems to have a very nice property. It actually works really well in practice, and it also has some nice theoretical properties. Okay, so in this case, you take xk plus 1 to be the analytic center of pk. Now, I should mention that this English here, the analytic center of pk, that's slang. That's informal, and it's actually not correct. Because the analytic center is not the analytic center of a geometrical set. It's you have the analytic center of a set of inequalities. And obviously, you can have multiple sets of inequalities that describe the same geometric set. And in fact, take your favorite polyhedron and add all sorts of redundant inequalities. The set hasn't changed. The analytic center has. And in fact, the following is true. Take a polyhedron and take any point in the interior of your polyhedron. So any point, just pick any point at all. I mean, it can't be on the boundary, but you take any point in the interior of the polyhedron. I guarantee, by adding redundant inequalities, you can make any point you like the analytic center. So that's, now you may have to add a large number of inequalities and things like that. That's true. But the point is you should remember that this is informal and it is slang here. So meaning it's just not right. Okay. All right. So the analytic center is this. It's the argmin, of course, of the sum of the logs of the negative. You maximize the sum of the logs of the slacks. These are the slacks in your inequalities. By the way, this is the same as maximizing the product of the inequalities. So it's exactly the same thing. You maximize the product of the. By the way, there's many other things you could do. You could do things like maximize the minimum slack. And if the AIs were all normalized to have the same length, for example, 1, that would correspond exactly to the Chebyshev center. Right? Because BI minus AI transpose X is norm, whatever it is. It's the distance. It's the distance to that hyperplane divided by the 2 norm of AI. Okay. Okay, so this works quite well, and we're going to go into that in great later today in detail. Okay, so for these cutting plane methods, there are lots of extensions. I'll mention a bunch of them, and then when we look at analytic center cutting plane method, we'll look at how these things work. So once you get the idea of that the only interface is a cutting plane oracle, then you can imagine all sorts of cool things. So you could do all sorts of things. You could do things like this. Your oracle, when you call your oracle with x, instead of just giving a single, I mean, there's tons of stuff you could do. Instead of just returning a single cutting plane, it actually has the, you could easily imagine something that returns multiple cutting planes. And I'll give you an example. Suppose, well, suppose you're solving an inequality constraint problem. The simple method would be this. You take your constraint functions and you evaluate each one. You have to do that. So you evaluate F1, F2, F3. And the first time you find an F that's positive, you call that F sub k, dot get subgradient, and you get a subgradient back. So that's one method for generating a cutting plane. But in fact, what you could do is if you sweep through all the constraints, you could then give the most violated constraint. But another option is to give all the constraints. Just give them all at once. And you just update your polyhedron and everything's fine. By the way, you can actually return not just, if you return multiple inequalities, you can actually return shallow cuts. So, and shallow cuts are fine as long as one of the cuts you return is actually deep or neutral, right? So it's still useful information. So let me just draw a picture to show how what that would look like. So that would look something like this. Let's see. And you might give some other kind of very colorful name for it. Here's your localization set. Here's a point. Actually, it doesn't matter. However you calculated it, CG, hit and run, Analytic Center, doesn't matter. What would happen is you call it here. And if you could do something like this, it could give you a deep cut. Basically says, don't bother looking over here. But there'd be no reason that it couldn't also give you a shallow cut like that. That says, don't bother looking here. No problem, right? So you just incorporate both. So that's how that works. And, I mean, that's kind of obvious. Actually, what's interesting about it is a lot of these things don't really make it work much better. Okay. Let's see. Oh, and then in this, instead of appending one, you append a set of new inequalities. You can also do nonlinear cuts. So you'll also find this talked about all over the place. And let's see, these would work. You could have quadratic cuts where you return that basically says instead of returning a half space where the solution, if it exists, must lie, you'd return like an ellipsoid, basically. And there'd be plenty of cases where something like this would work if your inequalities were quadratic or something like that. In this case, the localization set is no longer a polyhedron, but that doesn't really matter. I mean, in particular, things like ACCPM, they work just fine. So these are kind of obvious, and the ones, however, that are actually quite useful, and also quite strange and mysterious, is the idea of dropping constraints. So dropping constraints would go like this. After a while, you generate a big pile of constraints. So what happened was you started with a whole bunch of inequalities. At each step, you have added at least one inequality to your set. So what's happening is the polyhedron, the data structure that describes your current ignorance, is getting it's growing in size as you go. And that means, for example, whatever work you're going to do on it is also going to grow in size. I mean, it might grow linearly or polyhedrally, like polynomially, but it's going to at least it's going to grow linearly. So when you add these, there's the option of deleting dropping constraints. So then, how do you drop constraints? The most obvious thing is the following: here's your current set, and here are some redundant inequalities. So one obvious thing is to call a method on your current polyhedron, which is minimal. Okay, and what minimal does is it goes through every inequality and drops the ones that are redundant. By the way, how do you find a redundant inequality? Suppose I give you a polyhedron and I point to the 15th constraint. and I ask you, is it redundant? How do you do that? Any suggestions? How about the first one? How do I know if the first inequality is redundant in a polyhedron? What do you think? Got any ideas? What's that?
If it's linearly dependent on other columns?
That's no, that might be wrong because the B it connects in too. But that would be one. That's how you detect linear. That's sort of linear equality equations being dependent. But it's related to this. But there's actually only really one way to do this. How do you find out?
Can you solve like an LP and see if it's strictly feasible?
You got it. Here's what you do. You want to know if A1 transpose X less than BI is redundant. So here's what you do. Actually, there's some very sophisticated ways to do it, but this is very simple, basic. Everyone understands it. Here's what you do. You maximize A1 transpose X over the remaining inequalities. That's an LP. Right? Now, the optimal value of that LP is either less than or bigger than B1. If the maximum of this over B1 is less than B1, less than or equal to B1, what can you say about the inequality? It's redundant. So that's one way to do it. Otherwise, actually what that method will do is it will either produce a point that satisfies all the other inequalities but not that one, or it will produce basically a certificate proving that inequality is redundant. So, and actually to get back to your suggestion about linear dependence and stuff like that, there's more sophisticated ways. In fact, well, is it relevant? I don't know. That'd be a great homework problem in 364A, but I guess this isn't 364A. Anyway, the question would be, how do you find out if 5 are, you can think about that, by the way. How do you find out if the first 5 inequalities are redundant? You should think about that. Okay. Okay. So you could implement a method that was called, polyhedron dot reduce. And it would work like, it would just go through and solve one LP for each constraint. So it would check an LP for each constraint and drop that. Now, if by the way, the subgradient calls are fantastically expensive, the subgradient calls are cutting plane oracle calls. If the cutting plane oracle calls require a network of computers to fire up and the wind tunnel at NASA Ames to get fired up and all that kind of stuff, then no problem calling localization polyhedron dot reduce. No problem. But in a lot of cases, that would actually be too much. That would actually, to solve whatever K LPs would actually. Anyway, okay. So we're going to look. There's going to be some ways. There's going to be cheap ways to drop constraints, and there's safe and unsafe constraint dropping. Safe constraint dropping goes like this. You drop constraints that, without actually solving an LP, you know are going to be redundant. We'll see how that's done with analytics and cutting plane. Very, very cheaply. That's one method. And the other method is the unsafe method, is you just drop constraints whether or not they are redundant. Okay? That method works, by the way, really well. Capital N here. It seems sort of like the word on the streets is that if capital N is like 5 little n, everything's cool. And I mean, there are some proofs of this and all that, but they're I don't know. That's kind of people are, they're very complicated, as you might imagine. When you are dropping constraints that are not redundant, you are increasing the volume of that set. That's our merit function. So now the proofs get very tricky, and you have to show that your constraint dropping method is increasing the volume of the localization set more slowly or roughly than your cutting plane oracle, your cutting planes are reducing it. So that would be it. But the fact is that we'll see something like 3 to 5, capital N equals 3 to 5 little n works apparently very well. Okay. In fact, there's a shock. We'll see it next lecture, which is going to come up very soon. what's weird is you can actually drop constraints, and the method will do better. And that's a bit weird, but it's also just, it's true. It can happen. Okay. Another variation on this is a so-called epigraph cutting plane method. So if you have a cutting plane, well, it works like this. You put the problem into epigraph form like this. And what you're really going to do is get a cutting plane oracle for this problem here. So this is the problem. And what you want to do is you want to separate x and t. So x should be considered as your current proposal for x or something like that. And t is to be considered here an upper bound on the objective. And you're going to separate this from x star, p star. P star is the optimal value. Now the way to do that is this. If the current point is infeasible for the original problem and violates the jth constraint, you add a cutting plane that is associated with that violated constraint, and this is a deep cut here. Well, if that's well, I guess this is positive by definition. This is a deep cut here. This one where you get a subgradient. You get a subgradient of the violated constraint here, and this is a deep cut here. Now you could also just put this with 0 here, and that would be a neutral cut for the same problem. Now, if xk is feasible for the original problem, you can actually add 2 cutting planes. And the 2 cutting planes you can add are this. This is a deep cut here. This is a deep cut that you add in x and t here. And this here is actually something that says that the current point, that's the objective value, because it's feasible. T, which is supposed to be an upper bound on the optimal value, is clearly less than that. So you can add that one as well. So that's one. And this requires getting a subgradient of the objective. So that's the so-called that's how you do this in a. That's how you do this in. You can run a cutting plane method in the epigraph. Okay. Now you can also get a lower bound. We'll get to some of these in a minute. This is related to something called Kelly's method. But suppose you've evaluated a function f and a subgradient of f at q points. So, and just any, actually, sorry, doesn't need to be convex, but of course it has to have subgradients. So, what that means is that f of z, by definition, means f of z is bigger than this for all z. So it says that this is an affine global lower estimate on f. Okay? Well, obviously, if f of z is bigger than each of these, it's bigger than the max. So you can write it this way. And this piecewise linear function here, we're going to call that f hat. So you can think of, it's a very useful way to think of what it means to call, if you get a subgradient at a bunch of different points, a single subgradient will give you an affine lower bound. If you call multiple subgradients, if you get multiple subgradients at different points, for example, if it's an algorithm and your k steps in and at each step you've evaluated a subgradient, you actually have you now have a piecewise linear lower bound. And that's this thing. And I'll draw that. Well, it's kind of obvious what it is, but let me just draw it just to give you the picture of this. So here's the picture of that. I'll do it in R, which is kind of a stupid example, but you know. So here's your function. And let's suppose I've evaluated well, it's smooth, so gradient, sort of here, you know, and here, and, you know, here. Then what you do is you simply draw these first-order approximations like this. There you go. Something like that. And then this one looks like that. And this function right here that goes like this, that's a piecewise linear lower bound on your function. By the way, if you minimize that, you get this point here, and that's clearly a lower bound on your function. The point is that once you've evaluated a couple of, not a couple, but in fact n plus 1 subgradients of a function in Rn, if you've evaluated n plus 1 subgradients in Rn, then generically you can now produce a lower bound on that function, period. The cost is solving an LP. So what happens is this: if you replace f0 and fi by their polyhedral under approximators. Then solve this problem, which is an LP. Well, it's not an LP, but it can be converted to an LP. You know how to do that. So if you convert this to an LP and solve it, I guess this one's trivial, and this one you introduce one epigraph variable t. You get an LP. You solve that, and the optimal value is a lower bound. In fact, it's this value here. By the way, we didn't mention this. I'll mention it here because it's an interesting method. If you solve that LP, this LP here, oops. There we go. If you solve this problem, then you get a lower bound on the optimal value. And if this is your new point at which to query, you get a nice and you get a famous algorithm. So if your next query point is here, and it goes like that, that's called Kelly's cutting plane method, and it's actually quite a good method from the 50s, I think. I can't remember, either 50s or 60s, one or the other. That's Kelly's cutting point method, and what would happen is when you add this, your lower bound goes up there, here, and your next point is here, and you can actually see in this case it's a smooth problem that it's gonna do pretty well. It's not hard to show that it converges and so on. That's kind of, a small modification of Kelly's cutting point method actually makes it work really well in practice, and it's not clear from this picture why it wouldn't. But of course, pictures are generally in R2 and R3, and that's not where there's no interesting. It's not a problem. These aren't real optimization problems. Real optimization problems go down in like R10 minimum. They get mildly interesting in R100, and actually are real honest problems in R100K or something like that, where your intuition from drawing pictures isn't going to cut it. I mean, even close. So, okay. Let's see. So we'll go on and do the analytics ACCPM. Okay, so we'll look at ACCPM. I think this is sort of, I'm not sure, but I guess I would probably put this at the, if someone needed to run a cutting, needed to run one of these non-differentiable methods or something like that, you had a cutting plane oracle for some, and you actually really needed to do this, I think this is probably, depends on the situation, but this is probably the algorithm of choice. So, we'll look at that. And there's a couple of things we have to talk about. Okay, the first is just to remind you what the analytic center is. Again, this is not correct. Unless by, well, this is wrong. I mean, this notation universally defines P to be this set, and this is not a function of P. It's really a function of the inequalities. But we'll leave this and just understood that that's slang. So what you have to do is you have to maximize the product of the slacks in a polyhedron. And that can be done by Newton's method. That's fully, this is completely, this thing here is very smooth. It's actually self-concordant. So that means if you're going to give a complexity theory result for it, you're already, you're well on your way. And so here's the ACCPM algorithm. You start with a polyhedron. By the way, it doesn't have to be even a polyhedron, but it doesn't matter. You start with a polyhedron known to contain the target set. Then you do this. You calculate the analytic center. You query the cutting plane oracle. The cutting plane oracle can tell you that you're done, in which case you quit. Otherwise, it returns a cutting plane inequality. That's this. And that is appended to P, the description of P. Now, if this polyhedron is empty, then you can announce that capital X, the target set, is empty and quit. Otherwise, you increment K and repeat. So that's ACCPM. Let's see, now for constructing cutting planes, I think we've actually looked at a bunch of this before, so, but we'll go over it anyway. So if you have an inequality constraint problem, then you do the following. If X is not feasible, you choose any violated constraint and do it and add a deep cut. If it's feasible, you can do a deep objective cut. And the deep objective cut is given by you maintain the best value found so far, and you add this there. So that's a deep objective cut. How do you compute the analytic center? Well, you have to solve this, and there's lots of ways to do that. But there is one issue, and that's this. You're not given a point in the domain of this function. So that's actually the challenge here. And there's lots of ways to get around this. One, of course, is to use a phase one method to find a point in the domain. And that actually will have the advantage here of if you do that. The advantage here is going to be that this that will surely, in a graceful way, determine if this thing is empty. Then you can use if it's not empty, you can use a standard Newton method to compute the analytic center. You can also use an infeasible start Newton method. And there's one more method, which is you can actually solve the dual. You can do this. You do the dual of this analytic centering problem. And if you think about why that will work very nicely, you have a set of inequalities. The dual has a single variable for each inequality. If you add an inequality, you're actually adding a new variable to the dual. And so there the initialization is easier. So that's yet another method. Infeasible start Newton method. Actually, the truth is I didn't cover it really at all in 364A. It's in the book and stuff like that. But here it is. It's, all right, I covered it, but maybe too fast. You want to minimize this separable convex function subject to y equals b minus ax. So we introduced these new variables y. And the way it's going to work is this. The infeasible start Newton method does not require the points to be feasible. The traditional Newton method, you must start with a feasible point, and every direction you generate is in the null space of A, and so the points remain feasible. So it's a feasible method. Infeasible start Newton method, you don't have to be feasible. So here's the way you'd solve this problem: is you initialize x as anything you like, 0, the last x you found, some guess or something like that, and the radical method is to initialize all these y's to be, for example, 1. Why not? That's a point nice and squarely in the domain of the objective, which is the sum of logs. So you set all these. Now, when you do that, obviously this equality constraint is not satisfied. I mean, unless you're really, really lucky, unless it turns out that you're x. So this is the initialization. So here, let's see. Here would be a reasonable choice. Suppose you had a guess x previous. You could choose y to be the following. You would evaluate each bi minus ai transpose x, that's the ith row here. And if that's positive, no harm. Leave yi to be equal to that. If it's positive, it's in the domain of log y. And there might be like a little threshold value here. If it's small enough, you don't. Otherwise, you just set yi to be 1. So what happens then is these equality constraints here some are already satisfied. But any ones where this is not the case are not satisfied, right? So that's how that works. By the way, this infeasible start Newton method works. It's very cool. It has the property that if any constraint, literally coordinate by coordinate, is satisfied at any step, it will be satisfied forever afterwards. So, for example, if this is 100 inequalities, if there's 100 inequalities here, and 80 of these are satisfied immediately, but 20 are violated, or let's make it even simpler. Let's do cutting plane method. So in a cutting plane method, you just solved the problem with 99 inequalities. You added 1 inequality. Now you have 100. You satisfied all the 99 because you were actually at the analytic center of those 99. However, the new constraint you add, you for sure violate it. You might just have equal to 0. There might be just right on it. If it was a neutral cut, if it's a deep cut, you're guaranteed to violate that point. But then what's cool about that is only that one. You have 99 equality constraints here are satisfied, and only 1 is not, which is the new one. So everybody, anyway, okay. So the method works like this. You define the primal dual, the primal residual is y plus ax minus b. Now, of course, in a standard Newton method, you are always primal feasible. So you don't even have the concept of RP. RP is just 0 always. Initially, every step, RP is 0. And it stays RP because your Newton step is in the null space of A. So no matter what step you take in the null space of A, you continue to satisfy Ax equals B. In the infeasible start Newton method, that's false. RP starts off, in fact, it's guaranteed if the original point was not feasible, starts off non-zero. And the dual residual is A transpose nu and G plus nu. So these are the dual, the components associated with both X and also with Y here. Okay, so, and here the gradient is very simple to calculate. It's simply actually the vector, which is basically 1 dot over Y with a minus sign. That's the gradient. Now the Newton step is defined as follows. You actually linearize these equations at the current point, and then you get, and say that, and you linearize the equations, RP equals 0 and RD equals 0. Now, this equation is already linear, so there's hardly any linearization going on there. This one is not linear because G is a nonlinear function of Y. And you'll get something that looks like this. Now, H here is the Hessian of the objectives. That's diagonal. You get A and you get A transpose and so on. Now, that's a large system. This system is size, I guess, let's see, M. It's, let's see, this is I can't remember the dimensions of N and M, but let's see, Y is going to be M. So that's M by M. So this is not a small system here. It's quite big. However, this should be screaming structure at you, just like screaming at you with structure. There's tons of zeros, there's I's, this is diagonal, there's A and there's A transpose. So you should have an overwhelming and uncontrollable urge to apply a smart method to solve these equations. And in fact, you can do this by eliminating various blocks and things like that. So instead of having a complexity which is like cubic in M plus N, you'll actually do much, much better. What will happen is you can actually solve them by calculating delta X this way and delta Y that way, and so on. Now, when you calculate delta X, you have a couple of different methods for actually computing delta X. One is you actually form this matrix. And in fact, here you could do many ways. You could exploit any structure in A to form this matrix. But this matrix, you can, even if the matrix is dense, you can exploit structure in forming it. That would be one method. If this multiplied out matrix here, if this Hessian is actually, if this Hessian here is actually has structure, you could use like a sparse Cholesky factorization or dense or something like that. And the other method for solving this, and this would be probably the method that would be not frowned upon by people who do numerical things. You know, it occurs to me there should be a 2 here. So if you just simply work out what this is, this delta X is the solution of this least squares problem. If you actually form this matrix A transpose HA, I guess that's most people who do numerical things would consider that like a misdemeanor. It's called squaring up, right? So whereas over here, you never actually form this matrix, which has, I guess, whatever the square of the condition number of this thing here. So this is another way to do it. Now, by the way, the H halves don't have to scare you because they're actually diagonal. And this is nothing but a diagonal least squares problem. Okay. So here's the infeasible start Newton method. You start with a point X, arbitrary, and Y it has to be positive. So it could be all ones or that initialization we talked about before. You have your usual parameters. And what you do is you calculate the Newton step in delta X, delta Y, and delta nu. And you do a backtracking line search. In infeasible start Newton method, you cannot use the function value to do a line search. That's completely obvious because you're infeasible. So your objective actually can be very, very good. Very good. It's just totally irrelevant because you're not even feasible. And you really can't talk. It doesn't, anyway, it would make no sense. And in fact, you can easily see the method would fail because you initialize it at any point that's infeasible but has an objective value that is better than the optimal objective value, which of course is higher, well, because it requires feasibility, then if you did a line search or used as a merit function, the function value, you'd never get to the optimal point. You just, that would fail. Instead, what you do is you do a line search on the norm of the residual. And that's easy enough to do. I mean, the simple way is this, something like while y plus t delta y is not positive, you can do this. By the way, related to the question you asked earlier about the, it's actually much more common. In fact, well, it doesn't matter. You can either t times equals beta in a while loop here and simply find out if you're positive. But the fact is, you'd probably immediately, I mean, if you're writing this in a real language, like in C or something like that, what you'd really do is you'd go here, you'd get y and you'd get delta y, and you'd quickly calculate the largest t for which this is still the case. Okay? And if that, then you'd take that, the minimum of that t multiplied by, 0.99 and 1. So that would be your minimum thing. And then you'd check, you'd drop down to this one. And then you'd t times equals beta over here until this is satisfied. Okay. And then you update. Now there's actually some pretty cool things about this method. This method has the property, several properties. I'll just mention them, and actually you'll probably, I guess you will see them at some point soon. So maybe on homework 5, who knows? You'll see them. One interesting point about it is this: if you ever take a step size of 1, then all equality constraints become satisfied on the next iterate, and they will always be satisfied from then on. So that's one property. Another one is if any of the individual equality constraints is satisfied ever at some step, it will be satisfied forever on. I'd say that's unlikely to occur during the algorithm. So probably the better way to say that is something like this. Any equality constraints initially satisfied will remain satisfied during the algorithm. Then there will be a point at which you take a step size of 1, after which all equality constraints will be satisfied. So that's how that works. Okay. Oh, I think I already said all these things. There's a couple of things to mention. This method works does not work gracefully if there is no feasible point. Feasible means there's no point in the domain. So there's no positive y for which y equals a, whatever y was, y equals ax minus b or something like that. Is that it? B minus ax, y is b minus ax. There's no positive y that satisfies that. And then, of course, obviously what happens is the Newton method churns along. It obviously cannot take a step length of 1, because if it took a step length of 1, the next iterate would be feasible, but that's impossible, so it doesn't. So it does. There are methods you can do to recognize infeasibility and stuff like that, but I think the best way to say it is that infeasible Newton method is designed for things which are going to be feasible, and they don't gracefully handle infeasible things. Okay. Now let's go back to this pruning, and I can say something about this. This is also material from 364A and in the book, but it's a big book, and 364A we went way fast, so I didn't expect anybody to get it. So we're just doing backfill now. But these are actually very, very good things to know. So if you have the analytic center of a polyhedron, again, that's slang, then if you calculate the Hessian at the analytic center here, and that simply looks like this. It's nothing but this thing here. Oh, the gradient, of course, at the analytic center is 0. Obviously, that's the definition of it. Then it turns out the following is true. That defines an ellipsoid. In fact, let me say something about the other one. Let me say, because there's actually some very good things to know about these. These are in the book, I think, but I can't really remember. But anyway, here it is. Here's a polyhedron. Here's a point which is not the analytic center. Calculate the Hessian. That's this thing up here. The Hessian of the log barrier, like this, like that. That's not the analytic center. And this ellipsoid here is the set of x such that x minus z, make that z, transpose h, this is less than 1. Everybody got that? So you simply calculate that Hessian, right there, that formula, without the stars. There. You calculate the Hessian. This ellipsoid is guaranteed to be inside that set. Always. Whether or not you're at the analytic center. Actually, that's going to come up later because we're going to look at another interesting method. Very, very, very interesting method called the Deacon method. So at any point, if you calculate the Hessian, of the log barrier function, then the ellipsoid with a 1, defined by that Hessian, is inside this set, period. Okay? Now let's go to the analytic center. If you go to the analytic center, let's say that's here, okay? Then, well, this result holds because it actually held for any point. So if I draw the ellipsoid like that, I made it too small, by the way. You'll see why in a second. If I draw it with a 1, it's inside the set. And what this says is if I draw it with an m squared, no, I'm cool, because let's see, 1, 2, 3. How many are these? Let's see, 1, 2, 6. 6. So if I draw this ellipsoid with a 1, I'm inside it. This result says if I puff that up by a factor of m, which is 6 in this case, it will cover the set. Maybe I'm going to miss it anyway. I didn't draw it big enough. But theoretically, if I drew this right and I puffed up that set by a factor of m, I would cover the set. So if you calculate the analytic center, you get actually an ellipsoid. It's an ellipsoidal approximation of your polyhedron. And it's an ellipsoidal approximation that is within sort of a factor of m in radius. So that's in other words, you have an inner ellipsoid, you have an ellipsoid guaranteed to be inside, puff it up by a factor of m, guaranteed to be outside. Okay? By the way, the fact that this is guaranteed to cover the set is not, I mean, that's actually interesting because if I give you a polyhedron and I give you an ellipsoid and I say, would you mind checking if your polyhedron is inside my ellipsoid? That's NP hard because you have to maximize a convex quadratic function over a polyhedron. So you can't even check if a general one was. So in this case, there's a fast way to verify that this is true. I think this is easy to show, and it might even be, who knows? You may even do it yourself. Who knows? Okay. So what this allows you to do now, and you're going to calculate this if you use analytic center cutting plane method. You had to calculate this anyway because that's that AHA transpose. That's all that is. The AHA transpose thing. So you've already calculated all this stuff anyway, and it turns out that you can now define something, which is this irrelevance measure, and it's this. It's BI minus AI transpose X star divided by this thing. Here's what you can guarantee now. It's actually it's the normalized distance from the hyperplane to the outer ellipsoid. And I guess, I'm not even sure I need the M here. Isn't that right? No, I guess you do. Maybe we should make eta go between 0 and 1. Anyway, I don't know. So here's what you're guaranteed. If eta is bigger than m, then the constraint is redundant, and that you know without solving an LP. And by the way, it's super cheap because the fact is, I think you've actually already calculated. I think you've already calculated at the last step of Newton's method. I think you've already calculated all these numbers. So I think you have, but we can check. But I'm pretty sure you've actually calculated all these numbers anyway, or you're very, very close to getting them. Well, yeah, we'll leave it. You've just calculated a bunch of these numbers here. You have because you've actually factored. It's cheap anyway. You've factored this to calculate the last Newton step. So again, if you're doing direct methods, you've factored that. So once you've factored that, computing this is actually the norm. You have a Cholesky factor of that. This is the norm of L minus 1 AI, and that's one back substitution. Yeah.
The efficiency of this method, because we want to prune constraint when the number of constraint is really big, right? And
I don't know. Yeah.
If suppose I have a whole bunch of constraints and I want to prune them, then computing the hashing is going to be really painful.
Well, hang on here. If you have a whole bunch of constraints in describing P, I mean, the analytic center cutting plane method says you've got to calculate that Hessian. You have to calculate a Newton step to calculate the analytic center. So that's done. You're going to already be doing that. Now, what is true is that there's no reason to believe that any of the, this is safe constraint dropping. In other words, if you drop a constraint based on eta being bigger than m, it's safe. You don't have to avoid your complexity theorist friends and things like that, or the proof is still very, very simple because the pruning does not change the set. It changes the description of the set because you've dropped irrelevant inequalities. It does not change the set, so you can hold your head high if someone grills you and says, are you absolutely certain this method will converge? Then you can say yes. So that's the same. But there's no reason to believe actually that this will work. So in fact, what's generally done is you keep 3n to 5n constraints, and you just keep them ordered by this. So you drop the ones with you keep the 3 to 5n constraints with the smallest values of a to I. Now I can describe it another way. Let me describe it another way. So here's another way to describe this method. The method goes like this. In fact, it's a perfectly good way to describe it. It goes like this. Here's your polyhedron, like that, and you calculate the analytic center. Now you change coordinates so that the Hessian of the log barrier at that point is I. So in other words, and what that does is you make your set, you're rounding your set. You're making it more isotropic. Now what you know now is that a ball of radius 1 fits inside your set, but a ball of radius m is outside your set, covers your set. So that's what's happened. Okay? And so now the irrelevance measure is merely the length in those transformed coordinates. So you can say all sorts of interesting things about it. Actually, it says that no value of eta could possibly be less than 1. Right? It's impossible. Because at that center, the ball of radius 1 fits inside your set, and eta is the distance to the first hyperplane. So all the etas are bigger than 1. Any of the etas bigger than m are guaranteed to be redundant. So that's anyway, that's the picture in the transformed coordinates. Okay. Okay, and you get a piecewise linear lower bound. We can go through that. In ACCPM, you get that trivially because you get the subgradient. You can form the piecewise linear approximation and so on. We know this. And you can actually get this piecewise linear. You can actually get a lower bound in analytic center cutting plane method. That's not surprising because the analytic center cutting plane method calculates, an analytic center. But an analytic center is a step in a barrier method. So, when you finish a barrier method, you get a dual feasible point. We know that. That's the basic idea of a barrier method. And so it's not surprising that you're going to get a lower bound. And the details don't matter, I think. But the point is that this xk plus 1, that's the analytic center of the big thing, is going to satisfy something like this. And this is maybe better done in the notes rather than in the in slides. But anyway, you end up with a lower bound from all the stuff you just calculated. And it's based on the idea that you calculate an analytic center. Analytic centers are associated with central paths. On a central path, you've actually calculated dual feasible points, whether you know it or not. Dual feasible points means you have lower bounds on the problem. And so when you put all that together, that's the lower bound right there, which you've actually calculated. Okay, and ACCPM isn't a descent method, so you keep track of the best point bound and so on. And let's just take a look and see how this works. So here's a problem instance with 20 variables and 100 terms. So I guess it's a piecewise linear function. I think it's the one we've been using all along. So this is what it is. And I guess the optimal value is around 1. So that means 1% accuracy. That means 0.1%. And that means like 4 digits of accuracy. And this is f minus f star. Now, obviously, you don't know this at the time. we've basically found that well, in this case it's an LP, so you solve the LP to find F star. And then this shows you the progress. And you can see that it is not well, we can say a lot of things about this plot if you compare it to the subgradient plots. This appears to be, and that's actually correct, so there are proofs of polynomial time convergence and everything like that. This appears to be what people call linear convergence, right? Because that's a log scale. And, you know, there's like kind of a line that looks like that. And that means something like this, that roughly each iteration gives you a constant factor of improvement. You can work it out by calculating the slope there. Now, subgradient is very different. Subgradient, you're talking like 1 over square root k or slower convergence. And that doesn't look like this. It looks like that, and then it gets very, very, very slow. Okay. This is actually, if you trim and just look at the best point you found so far. We'll come back and look at some of these later. And this shows you the real effort. The real effort is the number of Newton steps required. And in fact, you can see here that the infeasible start Newton method at some point jams. So each of these is like a constant here, and the width of a tread is the number of Newton steps required to find a feasible point, and then calculate the analytic center. By the way, things like this, these are just appalling, right? That's 200 Newton steps or something like that. But this is sort of, you know, the amateur implementation. The correct method of dealing with this, which would have made this thing go like that, would have used something like a phase 1 there. So phase 1 would be like far superior. But this is just to show. And then this shows the bounds and everything like that. We're out of time, so we'll come back and get to this later. Although I will just show one more thing, which is this, and we'll talk about it next time, which is that if you drop constraints, you do very well. So, okay, so we'll just continue here next time.